In this topic, we're going to be looking at rate of chemical change. This is a topic in the chemistry paper 2. Within this whole topic then, we need to be aware of rate of reaction, and we're going to start by looking at how we actually calculate rate of reaction. Now, when we talk about rate of reaction, this is the speed at which a chemical reaction occurs, and there's a couple of ways that we can find the rate. This is really a measure of the quantity of reactant that was used up in a given time, or it can be how much product was formed in a given time. Be aware there's plenty of opportunities in this chemistry exam for unit conversions. So as a reminder, mass can typically be measured in grams or kilograms. Volume can be measured in centimetres cubed or decimeters cubed. But in this case, rate of reaction can be a measure of grams per second or centimetres cubed per second. You could even have, if it was a very fast reaction, kilograms per second. But in terms of a lab experiment, you're going to find this either in grams per second or centimetres cubed per second. So if we needed, for example, to find the rate of reaction when this volume of gas is produced in 2 minutes. So first of all, we will want this in seconds, so we'll convert that. We're going to do our quantity formed divided by time, and we'll substitute our values. So here our rate will be 234 divided by 120, giving me a rate of 1.95. Now I have done my quantity in centimetres cubed divided by time in seconds. So my unit will be centimetres cubed per second, volume divided by time. Another thing is that we could be asked to find rate of reaction using graphs. So for example, here we've got a graph where we can see time progressing and the number of moles of gas being produced. So we've got time, we've got product formed. So for example, between 0 and 180 seconds, we can see on this graph we made 0.0042 moles of gas. So we could do number of moles of gas divided by 180. Gives us a very small number, but it is the rate. Now because here we've done moles divided by seconds, that becomes the unit. So be aware that a really common exam question is that you might be asked either to plot a graph or interpret a graph and do a calculation. But I would expect 4 marks in your exam to be something along the lines of either drawing a graph or calculating a rate from a graph. Be aware that you need an axis that's regular interval apart. It might not start at 0, but you've got your time in seconds here and loss of mass in grams up the side. Just whichever graph you're drawing, make sure you label your axes. When you are drawing a graph, I'd recommend go through in pencil, go lightly at first. So for plotting, normally 2 marks for this, and you get a bit of leeway, but you need your plot to be within half a box of where it should actually be positioned. As I've said, go through lightly at first with a pencil. Go through, plot your points, taking care and time. It's really easy to make a bit of a daft mistake here. Once you're satisfied that you've got your plots in the correct place and you've plotted each, then go back through and check. Once you are then happy of right, I've plotted it, I've checked it, then go over in harder pencil. Once you've done that check for every single plot, then and only then draw your line of best fit. Remember that as far as chemistry or science as a whole is concerned, lines of best fit can either be curved or straight. So this one has got a bit of a curve to it. Generally, your line of best fit should be as close to all plots as possible, and you should have approximately half your plots on one side and half on the other if you can't get them fully on your line of best fit. One thing to avoid is drawing like a really jaggedy dot to dot. You won't get marks for it. So we wanted to use this graph to find rate of reaction. Between 0 and 60 seconds, for example, we can see how much gas we've made. So it's been 45, 6, 7, 48 centimetres cubed in 60 seconds. So we could do 48 divided by 60, And because I've done centimetres cubed divided by time, there's my unit. So we can find our rate either from data we've been given, but more likely a graph. However, that's an average over that time, and the issue, as we see in this graph, is that the line's not at a constant gradient, it's curved. So the rate is actually changing at different points. So if, for example, we wanted to know the rate at 40 seconds exactly, you need to draw a tangent. So this is a line that is straight, that has its central point at the point we're looking for, and it does not cross our line of best fit. It needs to be roughly parallel from our line of best fit on each point. So you wouldn't want it like really close here then aiming away over here. So you want it roughly parallel. Try and position it where it makes it easy for you to read values off. So notice I've deliberately ended at the 50 mark and kind of start at the 20 seconds, just in the hope and attempt of making this easy to read off. We then find our change in y and our change in x. So my time difference was 38 seconds for my tangent, and my volume was a change of 19 centimetres cubed. My rate would be my change in y over change in x. So here I've got my change in y was 19, my change in x was 38. I've got a rate at this point of 0.5 centimetres cubed. This kind of question will be worth 4 marks in the exam. 1 mark for drawing your tangent, another mark for finding your change in x and your change in y, a 3rd mark for doing change in y over x, and a 4th mark for actually getting the correct answer through. Even just drawing that tangent will get 1 mark, but it's always going to be y over x. So if we look here, we're asked to use the graph to estimate the rate of reaction at 60 seconds. So we'll draw a tangent for 1 mark, find our change in x and y, divide the two, so 8 divided by 40, which will give me 0.2 centimetres cubed per second. That's our unit because we've done centimetres cubed divided by time in seconds. Rate of reaction then can be affected by a range of different factors, but when explaining this, we need to be really aware and conscious within our explanations around why a reaction is actually happening. So there are 2 conditions that need to be met for a reaction to happen. First of all, particles need to collide, but secondly, that collision, the particles have to have enough activation energy. So if they don't collide, a reaction can't happen. But actually, even if they do collide, a reaction might still not happen because the energy needs to be there with those particles. This lends itself to an idea called the collision theory. So collision theory is actually the theory that states that for chemical reactions to occur, we need particles to collide with enough energy. And activation energy is the minimum energy that's needed for a reaction to happen. There are different factors that can affect the rate of reaction. This includes temperature, surface area, concentration, and pressure of reacting gases. Notice pressure of gases though, and also the presence of catalysts. It is an incredibly common question to be asked how any of these factors affect rate of reaction, and you can go into your exam assuming you're going to be asked at least 3 marks for this. What we don't know is if they're going to ask about concentration or temperature or catalysts. With concentration though, let's start with this as an example. Whichever factor they're going to ask you about, the best thing to do is approach this in a really systematic way. Say what happens to the particles, what's going to happen to collisions, and therefore what's going to happen to rate of reaction. It's a really good writing pattern to get into the habit of doing. So if we increase concentration, there'll be more particles in that reaction. If there's more particles, there will be more frequent collisions. The chances of a collision has gone up. And so that will mean the rate of reaction will increase also. It's worth mentioning here that we need to be really aware that as any reaction progresses, the concentration of the reactants will decrease. So in any reaction, what we tend to see is that at the beginning, the rate of reaction is really quick because there are loads of reactant particles colliding together all of the time. While, as that reaction continues and progresses, the number of reactants starts to now decrease because they're being used up. As a consequence, the rate of reaction will start to slow, and that's true for any general reaction that takes place. Next, for pressure. If we increase the pressure of gases, the particles are moved closer together. That's going to make collisions more likely, and therefore the rate of reaction is going to increase. For surface area, if we increase the surface area, we have more particles exposed to the reactant. So if we crush it, for example, that means that collisions are more likely, and therefore the rate of reaction for this will increase also. Temperature is a little bit more complicated. When we increase temperature, we do two things. Firstly, particles have more kinetic energy. This means they're moving around faster. Therefore, they have more frequent collisions and rate of reaction will increase. However, not only do those particles have more kinetic energy, but there are now more particles moving around that actually have enough activation energy. So the number of collisions will increase, but so will the number of successful collisions. So because now more particles have enough activation energy, the frequency of successful collisions has gone up. The final factor then is catalysts. Now, catalysts are a chemical or a substance that lowers the activation energy of a chemical reaction, but they're not used up themselves. Enzymes in biology are an example of a biological catalyst, and it's worth being aware of that different reactions need different catalysts. If you're studying separate science, this links into your earlier paper because the transition metals are really good examples of catalysts. With a catalyst then, they are changing the activation energy that's required for a reaction to happen. They're lowering it, and they do this by providing an alternative pathway for the reaction to occur. So if we're asked to draw this, here's a general reaction profile for an endothermic reaction. If a catalyst is involved, it will lower the activation energy, and so we'll draw a line that's lower than the original. So for catalysts and the rate of reaction, those particles have a lowered requirement for activation energy because the catalysts have provided an alternative pathway. Therefore, we have to be very careful about the way we word this. The frequency of successful collisions increases, and therefore the rate of reaction increases also. We now link this through to one of your required practicals in which you might be asked either to explain how to set up equipment, or you might be asked to interpret results from a practical. There are different ways of setting these up, and it depends on the products that are being made, the apparatus that you'll use. But here we see one setup. We have got two reactants in a conical flask feeding into a delivery tube that connects to a gas syringe. In this reaction, one of the products must be a gas, because what we're doing is collecting and measuring the volume of gas made in a fixed time period. So the idea here is that the volume of gas produced at a fixed time period will be our dependent variable. This is what we're measuring. There are loads of factors that we can change. We could change the concentration of the acid. We could change the temperature that we are having this reaction take place at. So if we're investigating, for example, how changes in concentration affect rate of reaction, we could set up the apparatus as we've just seen, and we'll add 10 grams of whatever one of our solid chemicals is into that flask, and we'll measure that with a balance. We'll then add a fixed volume, so for example 50 centimetres cubed of, let's say, hydrochloric acid, and we'll connect the gas syringe and we'll start a timer. We'll repeat this for different concentrations, and we'll pick 5 different concentrations. This is our independent variable. We will measure a couple of options: the total volume of gas made in 1 minute, Or you could, if you'd rather, measure the volume of gas every 10 seconds for a minute and you'll get like a curve. For our control variables, there's quite a few things that we can keep the same, but this really needs to be anything about any of the other chemicals whatsoever. So we could control the surface area of the reactants, the mass or volumes of the reactants we're using, the type of acid we're using, and the temperature that this reaction is taking place at. An alternative method is we could use the black cross method. Now this only works if we're making a solid precipitate in our reaction. And so when in class we're doing this, it tends to be we are producing or using sodium thiosulfate. So in this reaction, a precipitate, which is solid, is being made. And with our independent variable, we can change like concentration, masses, temperature. But our dependent variable is we are measuring the time it takes for this black cross to disappear. So in this method, we'll add 50 centimeters cubed of sodium thiosulfate into a conical flask. We will place this on top of a black cross that's been drawn on a piece of paper. And we'll then add a certain volume of hydrochloric acid, and we'll start timing this. Now here, if we're investigating concentration, we're going to repeat this with different concentrations of acid. Our dependent variable, though, is that we're measuring the time it takes for the cross to disappear. For controls, you could control your concentration or volume of sodium thiosulfate, your volume of acid you're using, your temperature of your reactants. You could even control the black cross, so its thickness and size. So if you're trying to figure out which is the best method to use for a certain reaction, my advice is look at the products. If we're going to use our gas syringe method, you want to have a reaction in which a gas is being made. If we want to use our black cross method, we need to have a solid being produced that will form this obstruction that we're unable to view that black cross. Note that an alternative method to anything with a gas is alternatively we can put this on a balance and measure the loss in mass. So that's an alternative dependent variable. We've kind of discussed this already, but as a reminder, collision theory is the idea that for particles to react, they need to collide with enough energy. And activation energy is the minimum requirement for a reaction to occur. So fundamentally, any of these changes that we make, if we increase collisions, we'll increase our rate of reaction. If we decrease our frequency of collisions, that rate of reaction will go down. So we know that temperature, pressure, for example, will all affect this. As a reminder, catalysts lower activation energy, they're not used up themselves. So if we were asked to draw a reaction profile, we want that line lower than the original. This is all done by catalysts providing an alternative pathway with a requirement for a lower activation energy. The next section of this is starting to look at reversible reactions. Now this is a chemical reaction in which the reactants make the products and the products can also make the original reactants. If we were looking or trying to identify a reversible reaction, look for this symbol. So a half arrow pointing right and a half arrow pointing left. We can affect rate of reaction and reversible reactions, and that's what we'll be looking at for the remainder of this session. So if we change conditions, we can shift what's known as the equilibrium, and we'll look at this in a moment. So for example, here we've got a hydrated copper sulfate, that's blue, and we've got anhydrous copper sulfate, that is white. As a note to this, anhydrous copper sulfate is a really good test for water. If we think water is present, it will turn blue when it becomes hydrated. But one thing to notice, to turn the hydrated copper sulfate from blue to white is an endothermic reaction that is going to take in energy. But to go from anhydrous copper sulfate and water to the hydrated copper sulfate is exothermic. So what we know is that if we have reversible reactions, one will always be endothermic, the other reaction will always be exothermic. Because the energy can't be created or destroyed. If it's been taken in one way, it'll be released through the other. This is where the idea about equilibrium starts. Now with equilibrium, this is the idea that we're at a point where the forward and reverse reaction are at exactly the same rate. So if we were looking at this, nothing would appear to be happening because both reactions are happening but at exactly the same rate. Now this can only be achieved in what we call a closed system. So this is where the reactants and the products are unable to escape. The next section is higher only, and this is where you need to be prepared to discuss what happens in a reaction if conditions change. And this is where Le Chatelier's principle comes in. This is an idea that if you change the conditions in a reaction, the equilibrium will shift to counteract this. So, for example, all the quantities of reactants and products we have depend on the conditions of the reactions. If you change something, the system will respond and counteract your change, and we'll look at some examples of this. We'll start with concentration. Now, if we were to increase the concentration of any of these substances, the reaction that we've added more of that reactant of will increase. So let's say, for example, if I increase the concentration of A, more of this forwards reaction will happen, and so I'm going to shift the equilibrium to the right. More of this will be used and more of this will be made. So if the concentration of reactants increased, more products will be formed. If we take away one of our products maybe, if I were to remove, for example, D, this reaction will slow. Again, the equilibrium will shift towards the right. More of this will be made to counteract that. So if we look at this, like when we're talking about rates of reaction, be really, really systematic in how you respond to this. State your change first of all. So in this case, let's say I've increased A. That's the change that's happened. Identify the reaction that will be favoured. So in this case, if I increase A, I'm going to favour the forwards reaction. This reaction will happen more. If this reaction is happening more, I'm going to shift the equilibrium to the right. So I'll make more of this. And actually the consequence is the amount of C in D will increase. Let's say now that my change is I decrease A. The reaction now that will be favoured will be the backwards reaction. This reaction will be happening more. And so therefore the equilibrium now is going to shift to the left. So this reaction is happening more, equilibrium will move away from it towards this side. Let's look at temperature. Increases in temperature favour the endothermic reaction. And so if we've got our temperature increased, we would expect this forwards reaction to happen more. However, that means that actually we'd expect the exothermic reaction to happen less. So the endothermic reaction is favoured when temperature increases. When we decrease temperature, this now favours the exothermic reaction. So the endothermic reaction will happen less, the exothermic reaction will happen more. So if we increase temperature, we're going to favour the endothermic reaction, and the direction of the equilibrium will shift towards the exothermic reaction. When we decrease temperature, we now favour the exothermic reaction, and the equilibrium will shift in the direction of the endothermic reaction. Pressure. If we increase pressure, this favours the side with more molecules. So for example, if I increase pressure, A plus B, there's 2 molecules here, there's more on this side. If I increase pressure, this reaction will happen more, I will make more C. So the rule of pressure is that if we increase it, that favours the side with more molecules. If we decrease pressure, this is the opposite. So now it will favour the side with less molecules. So if I decrease the pressure, that would favour my reaction involving C, and I would expect more A and B to be made. Equilibrium will be shifted this way. However, be prepared because occasionally there are some trick questions here. If we have a look at this diagram, what will be the effect of changing pressure on this reaction and why? Here, there would be no change to the reaction. A change in pressure relies on two things. You need to have a difference in the number of molecules on each side, and this doesn't have a difference, and so a change in pressure will not affect this. Pressure also relies on the substances being gases. So if you ever notice that it's a change in pressure but you don't have gases involved, or if it's a change in pressure and the number of molecules on each side is the same, then there'll be no change in reaction, and you need to develop that as to why. So pressure will only have an effect on equilibrium if the particles are gases and we've got a difference in the number of particles on either side. So let's say you had a question about a chemical reaction such as this, and you were asked to explain what would happen if pressure would increase. You would say nothing, because there's not a different number of particles on each side of the reaction. So if we look at this reaction, A plus B making C. If I increase my pressure, this is going to favour the side with more particles. So it's going to favour my forward reaction. So this forward reaction is favoured. The equilibrium is going to shift, in this case, towards the right. It's going to shift towards the reaction with less molecules. However, if I decrease the pressure, this will favour the reaction with fewer molecules, so this reaction now, and it will shift the equilibrium away to the side with more molecules, which in this case would be towards the left.